My name is Mark Madison. I'm here with Terry Wong. Today, we're going to talk to you about buffer solutions. We are doing chapter 14.6, problem number 5. So what is a buffer? A buffer is a solution that is used to maintain a certain pH range. It's not to maintain a neutral pH, but to either maintain an acidic or a basic range so that some organism or reaction can take place and not be affected by too high or too low of a pH. So we're considering a buffer made from 1 mole of HF and 1 mole of F minus and 1 liter of water. We are in 1 liter, so the concentrations of each of our components is 1 molar base and 1 molar acid. From an acid dissociation constant table, we picked up that the Ka of hydrofluoric acid is 6.8 times 10 to the negative fourth. Therefore, the pKa is equal to the negative log 6.8 times 10 to the negative fourth, which equals 3.16. We are going to use the Henderson-Hasselbalch equation to figure out the pH of our buffer. Henderson-Hasselbalch equation states that the pH is equal to the pKa plus the log of the concentration of the base over concentration of the acid. Plugging all the information that we have in, we have the pH is equal to 3.16 plus log of the concentration of our base, which is 1 molar, over the concentration of our acid, which is also 1 molar. This term, being log of 1, ends up to be 0. So at these even concentrations, the pH of our solution is equal to the pKa, which is equal to 3.16. So the reaction of our buffer is in equilibrium in a simple form between HF, aqueous, dissociating to H plus, aqueous, and F minus, aqueous. This is in equilibrium, so it's going back and forth in the reverse and the forward direction. So we want to see the effect when we add more H plus. So when we add more H plus, which is going to shift our equilibrium towards the creation of acid, indicated by this blue arrow right here, which if we shift the equilibrium towards the creation of acid, the pH of our buffer is going to decrease. Conversely, if we added a strong base, we would shift the equilibrium in the other direction towards the creation of F minus and the neutralization of HF, as indicated by this green arrow up here. That reaction is going to look something like this. HF plus our strong base with OH minus is going to create H2O and more F minus, creating more of our conjugate base, which will make our solution more basic and going to increase our pH. So we want to know what's going to happen to our buffer if we add 0.1 moles of strong acid. So let's draw our ice chart, which is going to be F minus plus H plus. It's going to give us more F minus. Because remember, when we add more H plus, we are shifting the equilibrium towards the creation of acid. So our initial concentrations from the very first slide is we have 1.0 and we have 1.0 molar of fluoride NHF. We are going to add 0.1 moles of H plus to our solution, which is going to react with the F minus, causing a decrease in the concentration of F minus by 0.1. We're going to increase the amount of HF by 0.1 because 0.1 moles of this H plus has converted 0.1 moles of the F minus into an additional 0.1 moles of HF. So at equilibrium, all this is reacted. We are going to end up with 0.9 molar F minus and 1.1 molar HF. Now we plug these back into our Henderson-Hasselbalch equation to get the pH after we've added 0.1 moles of H plus, which is equal to 3.16 plus log of 0.9 over 1.1, which our pH after this addition ends up to be 3.07, which is a minor increase. So let's see what happens when we add more H plus. To our initial solution now, we're going to add 0.5 moles of H plus. So let's go back to our equation. We still have 1.0 F minus, 1.0 HF. This time, we're going to add 0.5 moles of H plus, which again, this 0.5 moles H plus is going to react with half of the F minus. So we're going to have a change, 1.0 minus 0.5. Now, the H plus that reacted with the F minus now becomes HF, and so we have a change of 1.0 plus 0.5 molar HF. Which means, at equilibrium, all this has reacted. We end up with 0.5 molar F minus and 1.5 molar HF, which we are going to do the same drill, plug that in to our Henderson-Hasselbalch equation. That's a 0. And we're going to just do the same drill as usual. We have 3.6 plus log 0.5 over 1.5 is what our pH equals. So our pH for this step is going to equal 2.68. Now, probably the most important part of this video is how to hit a target pH. In this case, we're going to try to decrease our pH by 1 unit. So our initial pH, if you remember, was 3.16. Now the target that we want to hit is 2.16. So let's look at our equation again. We still have F minus plus H plus makes HF. But this time we're going to do this more mathematically. If we look at our Henderson-Hasselbalch, we have our target pH, which is 2.16, equals the pKa, which is 3.16, plus log the concentration of our base over our acid. So since we want our pH to decrease by 1, that means that this term right here has to equal -1. Because if we do a little bit of algebra, we have -1 equals the log of base over acid. So going back to our equation, is we have 1.0 still of F minus and 1.0 still of HF. And now we're going to add an unknown amount of H plus. So we're going to have a change. Remember, we are going to lose some of the F minus to that unknown amount of H plus, and we are going to gain an unknown amount of HF from that H plus. So our equilibrium concentrations are going to be 1.0 minus X and 1.0 plus X. Now, this is the concentration of our acid. This is the concentration of our base. So now, we just have to do some algebra and plug in numbers to this one to get our final pH. So we have -1 equals log of 1 minus X over 1 plus X. We undo this log function. We have 10 to the -1 equals 1 minus X, 1 plus X. Of course, 10 to the -1 is 0.1. So we will continue to do algebra that we learned way back in 6th or 7th grade. Cross multiply that up. 0.1 plus 0.1 times X is equal to 1 minus X. Now we're going to, again, continue to just do algebra to get ourselves into an easily solvable equation. And that ends up to be 1.1x is equal to 0.9. Divide through, and our x is equal to 0.82 molar H plus. So it looks like in order to decrease our pH from 3.16 down to 2.16, we need to add 0.82 moles of HCl to our 1 mole F minus and 1 mole HF buffer.